In the name of Almighty God, I'm Master Sankosha, and today I want to talk about molecular flow by the aid of radiofrequency power coupler combined cavitation diagnostics, which is related to nuclear instruments and methods in physics research section by the aid of accelerators, spectrometers, detectors, and associated equipments in order to identify safe operating regimes and to investigate the hydraulic behavior of the input power coupler, which is a part of the radio frequency cavities used at the synchrotron light source facility at the Paul Scherrer Institute. A special research program was established. Since 2005, 10 leak events occurred which led to accelerated downtimes up to several days. The aim of the research program was to perform conditional monitoring and diagnose fault regimes, which may lead to water to air and water to vacuum leak or task accidents. Since fault detection and identification are tasks of high importance for safe operation, practical operations, for data collection, cavitation, and possible structural rupture detection are discussed. The instrumentation which was used for detection of cavitation and observation of structural behavior consists of acoustic emission and structural acceleration sensors and a microphone. Noisy signals which capture cavitation, bubble grouts, and collapse events have been analyzed by various advanced time frequency methods. The third generation synchrotron light source or SLS is one of the main research facilities of the Paul Scherrer Institution or PSI in Switzerland. Since 2001, it provides synchrotron light to the international user community for research dedicated to materials science, biology, and chemistry. By now, it consists of 18 experimental sections, undulators, and bending magnets with 17 operational beam lines and reaches a high average availability of 97%, with a total beam time of about 6,720 hours and maintenance period planned shutdowns of about 2,048 hours per year. In normal operation, an electron beam with an energy of 2.4 gigaelectron volt and current of 400 milliampere circulates in the storage ring of the SLS. Four radio frequency cavities are installed in the storage ring to restore the kinetic energy of the electrons and to provide longitudinal focusing. These cavities of electron type and are operated at a frequency of about 500 MHz. Each cavity is powered with roughly 100 kilowatt radio frequency power from a klystron amplifier. The task of the input power coupler or IPC is to couple the radio frequency power from the coaxial line to the operation and operating mode of the cavity and also to separate the accelerator vacuum roughly 10 to the power of minus 9 millibar from the air-filled space of the coaxial line. As a power dissipation in the Cooper valves is about 40 kilowatt per cavity. Cavity valves, phalanx, and input power coupler IPC are therefore water-cooled. An identical cavity is also installed in the booster synchrotron, which accelerates the electron beam from the 100 megaelectron volt of the injector linear accelerator to the 2.4 gigaelectron volt in the storage ring. Since 2005, 10 water leaks happens in the cavity cooling circuits and cause annoying downtimes of accelerator operation. Water leaks to air type are occurred all at the cavity cooling circuits of the CF100 subs for vacuum pump, the higher order mode frequency shifter, and input power coupler. They appeared all at locations after a narrow band with inner radius of 1 centimeter. These leaks were repaired by Aramco Bond 2310. This cooler has a cure time of 2 hours at 66 degrees of centigrade or 48 hours at room temperature. One leak over 10 detected leaks was a water leak to vacuum type V and happened at the input power coupler of the cavity right at a 90-degree bends in the cooling circuit. When such leaks occur in one of the cavities, the input power coupler had to be replaced and the cavity vacuum backed and reconditioned with radio frequency power. If serious water leaks to vacuum occur in one of the storage ring cavities, downtimes of several weeks to months might be the consequence to restore the required ultra-high vacuum conditions again. Depending on the intensity of the leak, a major part of the vacuum chamber might have to be moved out from the storage ring, baked out, and then reinstalled. Such a scenario would lead to a downtime of several months since first, hundreds of bending and focusing magnets will have to be opened and then about 330 meters of vacuum pipe removed and put in an oven sector by sector for several days. They baked out at temperatures around 150 degrees of centigrade accelerates the outgassing of water molecules from the wall of the vacuum tubes required to each ultra high vacuum conditions. Again, another option would be to recondition which stored electron beam. However, this would lead to increased radiation level and reduced lifetime of the electrons due to the Toss-check scattering of the electrons on the residual gas. Therefore, all available preliminary measures must be employed in order to avoid these kinds of accidents. The cavity cooling circuits consist of copper tubes with diameter 8 mm for the CF100 stops and 10 mm for the thermally controlled cavity wall cooling circuit. These tubes are braced on the cavity stops and body built in copper. Since the distance to the inner cavity wall is several millimeters, water to vacuum leaks are unlikely for the cavity circuits. After an incident, in May 2008, the flow rates of the cooling circuits were double-checked and it was found that the flow speed of the de-inertialized water was as high as 8.5 meter per second at some circuits used for cooling of the flange and input power coupler itself. At such high flow rates, extensive cavitation and erosion can cause structural damage. Therefore, as a first step, the flow rate was reduced to 3.5 meters per second. In addition, a detailed coupled experimental and computational research program was launched. The main goal was to investigate the hydraulic behavior of the IPC under various flow conditions and to identify regimes without and with cavitation. Other objectives were the first one is testing instrumentation which can be online in real operation under non-hazardous and hazardous environment used for detection of operational irregularities and structural ruptures. The next one is testing buffer data acquisition, which they aim to capture and save only chosen events and to avoid continuous acquisition of large data amount at high sampling speed. After the reduction of the flow speed, the situation improved significantly compared to four water leaks in the year 2008. Before the reduction, only one water leak occurred in 2011 and 2012, each after a 2-day baked out period with a high water pressure and stress than in normal operation. As explained in the following sections, the reduction of flow rate shifted the flow regime below the cavitation threshold and reduced the failure rate. The experiment. During the experiments, reported here the pressure of the cover gas, the total mass flow rate, the pressure loss in the IPC, the pressure at the IPC inlet, temperatures at various locations, structural acceleration, acoustic emission, and sound data were acquired at the most interesting locations. The IPC is placed on a massive concrete block and connected to the water loop with flexible rubber pipes. The instrumentation used for hydraulic and structural tests included the following: The first is advanced time frequency analysis. Noise signals we capture cavitation, bubble growths and collapses, events for structural acceleration, acoustic emission, and sound pressure have been shown here respectively in this simulation. To come to simulation, the position of the sensors and properly chosen sampling rates are crucial factors, which need to be carefully selected before planning online monitoring or laboratory tests, as it is usually not possible to install instruments at the most relevant locations at the large significant scientific installations and meaningful online. The next chapter is discrete wavelet transform and denoising. The analysis presented here is devoted to the sound pressure data due to the following reasons. The first one is the microphone can be remotely installed. The sound acquisition is non-intrusive technique. The next one is events of interest are hidden in the signal. The signal to noise ratio is low. In case of cavitation fluid, the background noise of the sound pressure data, which is mainly generated by non-linear interactions between the coherent fluid structures and turbulence, is affected by the presence of collapsing. And the chapter of conclusion. In the asteroid ring of the SLS, four radio frequency cavities are installed with the task to restore the kinetic energy of the electrons and to produce longitudinal focusing. During several years of operation, a number of breakdowns due to the water to air and water to vacuum leaks have been detected. In order to study causes of such events and to define preliminary measures to be employed, to avoid these kinds of accidents, an experimental research program was established with the aim to identify these phenomena. And here you see the component and the geometry, which is a revolve cylinder, and also the parameters that have been defined here is temperature, molecular weight, inlet pressure, fraction of molecular pumped, and particle mass. And the definitions formula that we have defined here is molecular flow variables, influx, outflux, and transmission probabilities that there are formula by dividing of J out divided by J in, and J in and J out, which are inlet and outlet of the geometry boundary condition. You see that interpolation have been chosen by this sort of formula and expression. The next one is integration. You see the geometry for integration for input is here. The next is output is there. And we go to the two specific physical module that we have used is free molecular flow and mathematical particle tracing. In a free molecular flow, we have properties such as molecular flow, surface temperature, and you see the molecular weight of a species that in a parameter section we defined it based on kilogram per mole, and then surface temperature again we define the parameters. The wall that the geometry and boundary condition we determined in initial values properties which included incident molecular flux, pressure and number density, vacuum pump, reservoir symmetry, and then in mathematical particle tracing because we want to detect some leaks. And you see that we have a symmetry in our pump, and in mathematical particle tracing you see the fraction of incident molecule, and also it's possible to check the directly and pump speed with a specific boundary condition. There are two specific thermal emission and particle counts, and finally incident molecular flux, which shows the molecular flux from inlet to outlet, and the total number of density, total pressure, and the interesting part that I was mentioning is the particle trajectories and the leak that happens from the walls, and it's possible to detect it. Thank you so much for watching my tutorial video until the end, and also you can download this COMSOL simulation from github.com/masterscreen. Today is 10th of February 2026, and time is 5:24 o'clock in the afternoon.